Yeah, thanks very much, Raglan Drilling, for inviting Charles to present tonight. And yeah, like Alicia said, luckily I got here, so I should extend some thanks to Qantas. So yeah, the title of my talk today is the Julimar discovery, just on the outskirts of Perth. First slide there, just I guess it gets the exploration geologists exciting. Very much, this was a Friday the 13th of March. And you can see those black bags there just at the end of the run there. We're just into massive sulphide, and then of course we had to stop for the weekend because there was rain forecast. So a bit of angst over the weekend, but I'm pleased to say 500 drill holes later, we're still going. So I was probably a bit premature in getting worried about the project. But yeah, so anyway, that's yeah, basically how it all kicked off. And so I can just go to obviously normal forward-looking statements there. Just want to give a bit of an outline on the presentation today. Very much basically dividing my talk into these sections. Firstly, it's the pre-discovery geology and mineralisation in this area here, which is just on the outskirts of Perth. Yep. So this is what all the talk's going to be about today. So I guess just trying to set the scene. Now, why did Chalice get excited about this project? What was the telltale signs there that gave us the idea to come up with a target in this quite unusual part of WA? The next one is really spending a little bit more time on again what the geophysical signatures of this feature were. And this is a bit of a blow up there of what we call the Gonville intrusion now. And then I guess going through the early stage results, target prioritisation, and then obviously what you want to be doing early on is drill your best targets first. Then obviously will be most of the talk will be around the discovery, and then going into quite a bit of detail on the geology and mineralisation of quite a unique ore system here in Australia. Then just a slide or two on the broader Julimar complex, because we don't know too much about that yet. That's very much at our early stage exploration. And then finish up with a slide, what we think is a pretty good indicator there of the regional prospectivity of what we've termed the West Yilgarn magmatic province. So there'll be a little bit of description there of why we're excited about the regional upside. And there's obviously the massive sulphide. I've actually got some samples from the G1, G2 zones on the desk here, some core, so feel free to have a look after the presentation. There's some really classic sulphide textures there. And yeah, and we're finding a lot of this high sulphide style mineralisation within the system. So yeah, I'll kick off now. I guess just sort of setting the scene for the region. So this is the what we call the Julimar complex. Prior to our drilling, there was very little known about this quite prominent magnetic anomaly, and then the Gonville discovery is just off the very south of that. A bit of feedback there of this mag anomaly. Other areas of interest here I've highlighted, and I guess I just want to sort of set the scene that there were a few quite good indicators there of the regional prospectivity for this area. First of those was the Coates vanadium iron mineralisation. This was known since the 1960s. This is just out of Wundowie, so we're only 20 odd k's south of Julimar. And that's a classic titanium vanadium style mineralisation, which is hosted in a mafic intrusion. The other, I guess, more telltale sign was the Yarrawinda Brook prospect. This was discovered in the 1980s, and it was actually discovered by surface prospecting. It had a gossan, and the previous explorers there drilled off a fairly small but PGE-rich resource. And this is now in the hands of Caspian, and they're doing quite a bit of work around here and showing broad zones of disseminated nickel copper sulfides within a mafic, ultramafic intrusion. So that was already known in the 80s. We also had some earlier work there. Alcoa did some exploration. We're in one of their bauxite leases here, and they targeted another mag anomaly which turned out to be more this vanadium titanium mineralisation. And then company Best Bet, which is a Creasy company, they drilled 3 diamond holes just about 3 kilometres north of our discovery, and again they hit a lot of gabbro, a lot of mafic intrusive rocks. But they also did some broad-scale stream sediment sampling just on the east side of this mag anomaly, and actually got up to 19 parts per billion palladium in stream sediment. So there were a few telltale signs. And one that goes right back to the early 1970s, which was probably the most significant, was a company called Garrick Agnew. They were investigating the Coates mineralisation, and then on the basis of the old BMR aero mags, they went looking at other mag anomalies in the district and just took grab samples. Nothing more than that, but one of those samples in particular, which looks like it was very close to the Gonville discovery, had 1800 ppm nickel and 1350 copper, which is quite a high number for something of real significance in the nickel copper sulfide exploration space. And one other grab sample at our prospect called Bourdon, which is sort of central to this Julimar complex. Again, quite strong nickel, obviously ultramafic nickel values, and also elevated copper. But the intriguing thing is there's never any follow-up on any of these anomalies. The other work that was done, missing a little bit off the bottom here, but Geoscience Australia, they were back in 2016, they were looking at the Australia-wide potential for intrusion-hosted nickel copper PGEs. And the basis of that work was really a prospectivity type analysis, just looking at the broad-scale data sets. And that actually highlighted this whole western margin of the Yilgarn Craton as being prospective for these types of deposits. But again, there's only anomalous or low-grade mineralisation up at Yarrawinda Brook to really give you some encouragement that there was something going on there. So this was a sort of historic work, so definitely some positive signs there. However, when you go to the geology map, and this is probably what dissuaded a lot of people, is there's nothing mapped there. There's basically there's no basement geology, and it's all in basically a dissected laterite profile. So again, nothing to explain the magnetic anomaly. In terms of its geological setting, we can see we've got the Proto-Darling Fault to the west. We're only 15 kilometres inboard of that. And we've got the Chittering Metamorphic Belt, which is a high-grade basically amphibolite facies metasedimentary schist belt, and then the Jimpeting belt out to the east. This is quite a well-known metamorphic belt. It's about 3.0, 3.1 GA. So, but anyway, that's the limit of the geology. There's nothing over the whole Julimar mag anomaly to explain that. So I guess that probably left a few people wondering, really, is there anything of significance there? The other part, I guess, when you're exploring for these types of deposits, you've got to have a model in mind, and you certainly got to have the basics there to understand what you need to look for in practically geophysical data sets to give you a good idea of prospectivity. In terms of these styles of deposit, one major feature of them is they're on craton margins. That's a very important regional scale control on the location of these systems. And that's really because of this favourable lithospheric architecture. There are weak margins of Archean cratons. These magma pathways can find their way up, and there's plenty of potential there to form deposits at many different settings or local accumulations of sulfide within these magma pathways. So we've already seen we're in the right regional setting, craton margin, and then what sort of intrusions do you look for these types of deposits? You look for small ones. That's just about the giveaway there. They can be tens or hundreds of metres in thickness, and also what they tend to have is this this high aspect ratio, which is big long axes compared to their surface area. And there's some classic ones shown on the right-hand side here. These are schematics of well-known orthomagmatic sulphide deposits. You've got the Norilsk deposits here. These intrusions are only 300 metres thick and only a few kilometres in lateral extent. But going down the axes here, there's a huge amount of mineralisation within these relatively small intrusions. And then other examples in Australia, Savannah and Nebo Babel, these tubular or dike-like morphologies. So small intrusions and these particular shapes to intrusions are pretty much the hallmarks of what you want to see in your geophysical data sets. In terms of mineralisation, again, we didn't really have much of an idea, I guess, of the geology at this stage, but obviously dense sulphide melts. They prefer to collect or accumulate around margins of these intrusions, particularly the base. And there's a few examples there: Jinchuan, the Taunak, and then Voisey's Bay is a little bit different. So the other favourable setting there is where these dikes enter magma chambers. There's obviously quite a fluid dynamic change happening at this point, and that's where a lot of sulphides can accumulate. So yeah, so we want to be looking at certain intrusions, and we want to be looking practically along the margins of those intrusions. In terms of grades, they're a factor of many processes, but I guess the main thing to say here is that you can get quite a bit of variable grade even within one deposit because of the ratio of silicates to sulphides, the sulphur source, whether it's all from mantle or the local crustal rocks there, and you can also get sulphide melt fractionation. So those are pretty important things in terms of primary settings, but one that gets probably a bit neglected is the post-depositional overprints. These can change where you find ore deposits. The sulphides being weak can get mobilised off into the country rock, and you don't have to have just a perfect sort of situation like this where sulphides are just sitting nicely within an intrusion. So you want to be thinking about these sorts of processes and what the deposits can look like, particularly when you get into older terrains. So that's pretty much the backdrop there for what our thinking was and what led us to peg this ground. So in 2018, basically we did two exploration licence pegs, one to the south, which was a bit complex because we were in farmland and we did want to peg into the forest, and then the other one was basically 99% forest there. So fortunately for us, most of the ground amenable to exploration was on cleared farmland, so that meant we could get in on the ground very early and do the usual sort of work. So we interpreted this feature here, which sits just off the south, as being potentially a conduit, a chonolith style intrusion, relatively restricted strike length there, about 1.8 kilometres, and maximum width about 900 metres. So that fitted our model quite well. Want to look for one of these well-focused conduit style magmatic systems, and that's a great place to start. So initial field reconnaissance, we couldn't find any outcrop, so we couldn't explain the magnetic anomaly. But again, given our target was massive nickel copper sulphides, these are very responsive to electrical methods, EM geophysics. So we basically run 200 metre space traverses right across this. And this is all basically cleared farmland, so it was pretty cheap and easy to do. And the results of that survey are highlighted here. The yellow plates there are the high conductance EM conductors there. So we identified 4. We had A just along the northeast margin, quite a long strike extensive conductor. We had E, the strongest one, which is a smaller plate just down on the south western side of this mag anomaly, and then an internal one here and here. So they were the conductances that get us excited when we're looking for sort of massive or semi-massive sulphides. And we deprioritised these other EM plates because they were the order of hundreds to 1,000 Siemens. So we didn't think there was much going for that, but that certainly turned out not to be the case. So we've got these EM conductors. We decided, well, probably the best way is to screen them with surface geochemistry. and we did two surveys here, fairly tight lines, 100 metre space lines, 25 to 50 metre samples here and up here. And certainly we got a response. Our peak response there was 690 nickel and 1800 ppm copper, which again is a pretty high number in terms of the copper numbers. So there's quite a coherent anomaly here and more of a patchy anomaly up to the north. And most of the reduced response is there's actually quite a bit of sand cover up here, which we wouldn't have thought. But it's almost like bricky sand, you know, there's just loose sand just sort of sitting in sort of channels sort of all over this area. Topographically, we're in an undulating area here, but it was quite surprising to see so much sand just sitting on top of laterite. So I guess, you know, we'd done the EM, we'd done the soils, and on the basis of that, we designed a 1200 metre RC program. The idea being we'll test our strongest conductors. So the first hole was going into conductor E, and then we'd move up to A, and then obviously work through our priority list. So that was the start of it. So hole 1, out in the paddock, basically targeting this high EM conductance plate. And and as you would have seen from that first slide, we got pretty excited almost from day one, and ended up hitting an intersection there, phenomenal intersection there, 19 metres, 2.6% nickel, 1% copper, and the PGE grades were, you know, really unbelievable. You know, we're looking at over 8 grams palladium and a gram platinum, and this is all from, you know, 40 metres depth. There's some of the chips. So yeah, it was a pretty exciting weekend there, and then early into the next week. Geologically, we saw there was a serpentinite above the ore zone here, and then below we went into a mixture there of serpentinite and gabbro. So initially our idea was that maybe this intrusion's overturned, and the base, you know, where we're getting these high-grade sulphides was sitting quite close to the base. But as we drilled, we found that wasn't the case. So that was down here, conductor E. So after all that excitement, we moved the rig right up to conductor A, just drilling the shallow up-dip plunge there of that conductor, and basically that didn't hit much. It actually hit a lot of disseminated sulphide, but at the time it didn't look that exciting, and we hit basically sulfidic sediments just on that eastern margin there of the intrusion. So geologically it looked interesting. Then we went to conductor B, drilled a hole there and got massive sulphides internal to the intrusion, and then we went back down to the south here. We were just getting, you know, results coming through. We had a PXRF, so we were, you know, zapping every sample madly, and that brought us back down to this the discovery area here. We drilled a hole to the east, and there was no EM out here, but we drilled a hole on the basis of some interesting geochem. You know, one of those surface geochem anomalies was just sitting right up on this slight hill here, and we hit another beautiful intersection there, 40 metres of, you know, 2 and 3 grams PGEs, 0.5% nickel, 0.5% copper. So yeah, so that, you know, they were the heady days in about the first month. We drilled our first diamond hole, which we got for free. Didn't hit anything, so don't take free drill holes. And then we were a bit concerned what the EM was telling us, and we designed a hole that would go down the axis of what was modelled as the EM plate, and that hit pretty much continuous massive sulphides. So yeah, so it was pretty exciting times, and I guess we're still drilling, so, you know, things are going pretty well. So that was really the sort of history there of the discovery. Obviously, we're doing a lot of logging and trying to understand the geology, and we were seeing there was a lot of fine-grained serpentinite, so a lot of quite tricky geology there to try and break up and understand, you know, what's going on internal to the intrusion. So just late last year, we got Tony Crawford involved, and Tony's a well-known petrologist, petrographer, and we started looking at our analytical data in a bit more detail. We're doing quite broad ICP suite analyses there of all our rock types, all our samples. And so what we wanted to do is just look in detail at our major element trends there to see if we could break up the geology into the component rock types. So this is all our sampling that we had available. There's about 90 RC holes and about 20 diamond holes. And what we were finding was a lot of them were plotting in this orthopyroxene olivine field, which is known as a Harzbergite. So a lot of our early samples there were intersecting these sorts of rocks, but we're also finding there was a trend up to the plagioclase end member up here on the aluminium axis there. And so we were seeing Harzbergites into pyroxenites and then going into gabbros. So we were actually seeing the normal, mafic, ultramafic suite of rock types that you'd expect in these sorts of intrusions, but they were quite tricky to identify there from just, logging lots of serpentinites. So that's the sort of range of rocks that we're seeing, and we're seeing a slightly wider variety now that we've drilled a lot more holes over the intrusion. But one thing we noticed, we're not seeing any clinopyroxenites, whirlites, troctolites. These are all clinopyroxene sort of end member rocks there in intrusion. So it's very much an orthopyroxene signature, which is a high silica, high MgO rock. Just in terms of how we ended up breaking up the rock types on the basis of that, we decided to use MgO, which is basically olivine versus other minerals in the intrusion. And that gave us a really good breakdown there, and at least in the major element classification there of our main rock type. So the most magnesium ones we call SP1, and if you see some of our more recent releases, you see we've used this terminology. So that's greater than 35% MgO, goes up to about 40. And then the next group below that is 30 to 35. So that's that light blue field here. And then when we get into the pyroxene bearing rocks, the MgO is dropping as well. So we've got two groups there of pyroxenites. And we've got another little weird one here called a low nickel orthopyroxenite. You can see on that nickel versus MgO, there's a cluster of rocks just forming, sitting below the normal range of intrusion rocks, and that's geographically quite separate as well. And there's the yellow fields there are the gabbros, which is a pretty general term that we used early on, and now we're starting to divide those up into their component rock types. So it goes right through to basically an orthosites up this very aluminium-rich low MgO end of the spectrum there. So what we noticed really from these major element trends, and it's the same with the minor elements, is that there's a coherent trend there from olivine rich to olivine poor, and they're well represented right across that spectrum. And we believe that they're really a co-magmatic suite of rocks there that we're seeing internal to the intrusion. Now just a couple of slides in a bit more detail on those rock types and mineralisation within Gonville. So that's the geology as it stands, based on close to 500 holes now, with the majority of the drilling still in the southern part, but we are pushing drilling up into the north as well. And so those rock types that I showed you on those charts have quite a well-defined geographical spread. So SP1 is this purple unit here. So that forms like the core of the intrusion. It's approximately 250 metres wide, and it has quite similar chemistry right across there. And these are sort of typical values that we see in SP1. MgOs, up to 40%. The nickel in that 1,500 to 2,500, and chrome pretty much at the same spread as well. And very low other major elements, because it's just basically an olivine-rich component there. And like I said, it's consistently the central part of the intrusion. And another thing, it has very consistently elevated palladium. So very, very hard to find a rock that hasn't got more than about 0.3 ppm palladium. So the whole intrusion is very PGE endowed. SP2, which is that less magnesium rock, tends to form, that's this pale pink or pale colour anyway, just on the margins there. So that's the next most dominant rock type. Again, that's sort of the order of 250 metres thick. And most of our mineralised zones are actually within that SP2. So you can see there's a clear association with what we call these high-grade G zones, which are 11 of them now. They seem to be better developed in this SP2. The other rock types that we see, again, quite well understood geographically now, are these pyroxenites. and they tend to form a unit, which this is mostly low nickel peroxenite on the western margin, but we're also starting to see peroxenites develop on the eastern margin, which is the footwall of the intrusion. Gabbro-norites and orthosites tend to be developed up in this northwestern corner where we've extended the drilling out across this package. But you know, we still haven't really chased the margins yet of the intrusion out to the west. That's what we're doing currently. And like I said, you know, these G1 to G11 zones, we tend to see two main types of association there. One with a high base metal, we know high nickel, copper, and then others with very low sulphur, low sulphide abundances, and they tend to be more pyrrhotite dominant. So these high-grade zones are pentlandite, pyrrhotite and chalcopyrite with an abundance there of PGE phases. So the next slide is just some sections through the Gonville intrusion at various northings there. Again, just to emphasise the broad mythology of the intrusion. We're down at the south here. You can see that the SP1 is the dominant rock type here. We've got SP2 around it, and we're getting some of these G zones internal to SP1. And then you can see here is the high-grade G1, G2. It actually coincides with an internal gabbro, so there seems to be a break in the intrusion at that position. Moving further north, you can see the G1, G2 zones. We've chased them down to depth now, and they're still open. And then we're finding, as we've stepped out to the west, we're finding more parallel high-grade zones within this SP2 unit. So certainly a lot more potential to extend these zones out to the west and at depth. And then going further north, you can see the SP1 starting to filter out a little, but we're still getting these high-grade G zones, and we're starting to see something develop right on the eastern side, where the contact seems to be laying down a little bit flatter here. And then going to the north again, more broad disseminated style mineralisation. So overall, so that's the intrusion. On the footwall side, we have sulfidic sediments, and they tend to be forming right on the margin of the intrusion. And then on the hanging wall side, we don't see too much of it, but there's a mixture there of amphibolites and gneisses and felsic metasediments. So that whole package there is of the order of up to 800 metres thick within the intrusion. Other I guess, overprints there. You'll see there's a lot of granite to the south. So there's a big batholith there that seems to have starting to stope out the intrusion on the south side. But that seems to disappear quite quickly to the north. And then we've got these green units there, a Proterozoic dolerite dike. So there's a lot of post-mineral diking, right through the area. The other thing to point out, like we'll see when I go through a few more detailed rock slides there, is this pervasive hydrous metamorphic overprint. So all the rocks now, there's almost no igneous mineralogy. What we see is a lot of serpentine after olivine and amphibole after pyroxene. So a lot of retexturing has gone on since deposition. And like I said, there is a bit of deformation as well. There are some brittle, narrow brittle and ductile fault zones through the intrusion, but mostly it's just a retextured sequence of olivine-rich rocks. So now a few slides just on the mineralisation. It's probably what you're most excited about. This slide here is a perspective looking down the intrusion to the northwest, sort of give you a bit of an idea of the spread of mineralisation within the intrusion. And then there's a few key photos there, and I've got those samples here on the desk here to give you a good idea of how the mineralisation looks in hand specimen. So as I said, there's certain styles of mineralisation within Gonville. The most obvious, which was obviously the early EM targets, so these high sulphide, or up to 100% massive sulphide. So these are forming this G1, G2 zone, which is internal to the intrusion against an internal gabbro. There's quite a association there. As the sulphide abundance increases, so too does the grade. And with the massive sulphide peaking at about 3.5% nickel and about 1.5% copper. So there, that's the G1, G2, and then we also have quite a separate zone, what we call G4, and G4 is quite close to the base of the intrusion, and this has a slightly different metal association, tends to be more of a PGE copper dominant system, and this is a bit hard to see here, but this is basically disseminated chalcopyrite through here, and this goes up to 3% copper, so you can have some very high copper mineralisation, and that tends to have PGEs and gold as well. So quite a different association down on the footwall contact. So we've got these multiple lodes or zones through the intrusion, and they tend to be defined by gradual increases in sulphide abundance. So where we got low sulphide mineralisation, it's really a bit of a grade cut there. But typically we're defining greater than 1% palladium as high grade, and the sulphide abundances are much lower, in 3 to 10% sulphide. So that tends to be these G5, G5 to G11 and G3 zones internal to the intrusion. And we find that this mineralisation can be hosted in quite a variety of rocks. It can be in the SP2s and the peroxenites and even the gabbros. And then the other intriguing part, I guess, of Gonville is this very widespread low-grade mineralisation. This is in the order of 0.3 to 1 gram. It's not unusual to get 100, 150 metres width of this type of mineralisation, but again, the sulphide abundances are relatively low in that 1 to 3%. So that's the sort of spread of sulphide mineralisation we see within Gonville. The other point is that there's a very prominent oxide profile over this intrusion as well. And this starts from surface even and under some of that sand cover. And the depth of weathering, a bit hard to see here, but it's around about 30 metres from surface to the top of fresh rock. So this oxide zone's developed principally in saprolite over the more ultramafic dominant rock types. The other point to make about the Gonville is that the nickel-copper ratio is quite consistent at about 2.5 to 1, where we've got a lot of sulphide. And throughout the whole intrusion, there's a very constant ratio there of palladium to platinum, about 5 to 1. So something at the scale of the intrusion is given a very consistent palladium-platinum grade, right across this what is a very dynamic system here, and pulsing in different zones of mineralisation, through a large part of that intrusion. So there's something there to understand. We're probably fair to say we don't understand that yet, but we're certainly seeing a lot of macro scale grade variation in terms of base metals, but the PGEs seem to be much lower range of grades. So that's the sort of setting the scene really for what you see in the scale of Gonville in terms of the overall geology and mineralisation. I've just got a few slides just to show why we're obviously describing these as intrusions, and that's basically we do see not very commonly, but these are original olivine cumulate textures here. So this rock's been 100% serpentinised now. But you still see these lovely olivine outlines like you see in a lot of komatiite systems. So there's this progressive change in textural preservation. These rocks are just serp magnetite, but in certain areas there, for whatever reason, we are seeing preserved textures. And the mineralogy of SP1, because it's olivine rich, is just about always serpentine magnetite with very minor amphibole. And the only other major phase there is chromite, and that's again an igneous mineral as part of this, the original mineral assemblage. SP2s, you see a bit more amphibole coming in, and a good example here are these big coarse amphiboles after pyroxene. So these are orthopyroxenes, and you can see they're pseudomorphed quite well by the fine amphibole meshes there, but there's still a lot of olivine cumulates as well. So the mineralogy here is similar, but we're starting to see a bit more amphibole come in, and that's because of there's actually pyroxene in these rocks as well. So that's SP2, the peroxenites. Again, you get some very coarse pyroxenes, they're original pyroxenes, but they're pseudomorphed by this felted mass of amphibole. So when you look at them in hand specimen, you can just make out the coarse pyroxene textures, but everything is amphibole. So again, the whole range here, just the sort of masses of amphibole and chlorite, but still lithogeochemically, these plot in the pyroxenite field. So yeah, a range there of textural preservation. Pyroxene 2. The only dominant difference there is there's no olivine in these rocks, so hence no serpentine or magnetite, but you just get these lovely coarse pyroxenes in places. Other areas it's all replaced by fine amphibole chlorite mesh. And then the low nickel pyroxenite, it's still got olivines in it, but again, it's very much an amphibole serpentine rock, but certainly no evidence there of anything other than orthopyroxene. So again, these rocks are a bit easier to tell in thin section than they are in hand specimen. The exception I would say would be the more gabbro, norite, leucogabbro rocks. These still have a lovely coarse plagioclase phenocrysts here, not still plagioclase, they're actually replaced by clinosovicite, but texturally they're still quite well preserved. So a little bit more textural preservation within this group, but yeah, certainly in the hand specimen they're a little bit easier to see. So I guess I've just given you, an overview of Gonville, overview of the mineralisation, and what's going on down there. Now to put it in context, looking now at the Julimar complex. Basically, we've only done early stage exploration up here. We're hoping to be drilling there later this year. But essentially, what we've done now is quite comprehensive regional scale surveys. I guess the most interesting of those was our early airborne EM, which we flew late last year. At that stage, we'd obviously defined mineralisation at Gonville, so we knew that would respond well to an airborne system. But then we saw this huge trend extending to the north there, what we call Hartog, and that we've done the ground EM over that now, and there's 30 EM plates come out of that survey. So something very strong there in terms of EM signature just directly north of Gonville. We also had some lower order, but still indicative of likely bedrock responses to the airborne EM up here at Jans and Bourdon. And then and now we've actually taken geochemical soil samples all the way along that trend, and you can see we're getting some nice nickel copper anomalism there, showing there is definitely some more ultramafic packages within what was that original Julimar complex magnetic anomaly. We've also done ground gravity. Again, there was always one sample out here from the regional survey work that had a very high gravity response, and now we're sort of seeing that at Hartog we're getting a very good coherent gravity anomaly there, and that extends all the way up to Bourdon. And then up in the north there, at a place called Drummond, we're getting the gravity kick in again very strongly. So this is all the data we've got at the moment for elsewhere in the Julimar complex, but we're certainly seeing similar EM responses to what we see down in Gonville. And that had a relatively subdued soil response. Early on, it wasn't a real bull terror there, unless we took samples right over the outcropping mineralisation. So yeah, and there's quite a lot. This is all laterite covered, so we're dealing with quite a complex regolith profile going north. So yeah, so obviously can't wait to be drilling up into the Julimar State Forest, and yeah, we've got plenty of good targets to be hitting up there. So that's pretty much the detail. Just got one slide really on what we call the West Yilgarn Magmatic Province. Obviously, since we pegged Julimar and got our first result, we went on a bit of a pegging spree, basically all the way up on the western margin there of the Yilgarn Craton. We've done a lot of in-house compilation there of geology and geophysics, and our interpretation, we believe there's potentially hundreds of intrusions up this western margin of the Yilgarn. And some of those appear on some of the state maps, but most don't. And I guess just while we're on that topic, the 250,000 geology sheets which cover this area here are all mapped in the late 70s to early 80s. So they're really quite dated there in terms of you know, our broader understanding of the geology of the Yilgarn Craton. You know, obviously they were done at a time when probably didn't realise the significance of finding you know, mafic, ultramafic intrusions in this neck of the woods. So yeah, so there's certainly room to improve the geology. Our first work up at Barra Barra here, we've already identified a 4-kilometre long magnetic anomaly which has good soil nickel copper chrome anomalism, and you know, we're hoping to drill that fairly shortly. So that again is more indicative of the scale of, you know, what we're dealing with here with a big, you know, large magmatic system. There's some new data come out from the Geological Survey. Basically just earlier this month, or in July actually, they put out a new release, and they've under this accelerated geoscience program, and they've provided a new geomag interpret this whole southwestern terrain here. They've got some new dates and some new isotope data as well. So there's starting to be a little bit more data come out of this area now, which will help us, you know, understand the broader significance of what we're seeing at Julimar. There you know, really is a significant opportunity to revise the geology here. You know, as we saw, Julimar magnetic anomaly was just unclassified there, you know, only a couple of years ago. The survey are flying a regional survey, the Murchison survey, which will cover a lot of this area, but on very broad space lines. But there will be new information coming out. And why is that significant? Well, if you look at the southwest Yilgarn, we've got 3 world-class deposits now. So we've got Boddington, just down in the Saddleback Greenstone Belt, just south of Perth. We've got Greenbushes, the lithium, you know, the spodumene pegmatites down in the southwest, and now we've got Julimar, you know, PGE discovery there, just on the outskirts of Perth. So this southwest terrain might have been regarded as a poor cousin, you know, perhaps you know, to most people exploring in the Yilgarn, but you can see you've got world-class deposits here, and we believe that this West Yilgarn, you know, the West Yilgarn magmatic province is certainly going to deliver, you know, new discoveries going forward. So the next slide is just really one to finish on. As an explorer, you always want to understand, you know, why no one else found something before you did, and I guess you know, there's reasons for that, and I've sort of highlighted them really. What are the strengths and what are the weaknesses? Because, you know, when you're conceptualising about a project, you only got a couple of pieces out of the jigsaw puzzle to go on, but some of those are quite important pieces. And I guess the first strength was Yarrawinda Brook, discovered in the 1980s. So there was already indications there of orthomagmatic sulfides in the district. When we had a look at Julimar, you know, we had a very prominent magnetic anomaly which hadn't been even drilled, let alone explored, and you know, with a little bit of you know, proactive you know, conceptual geology, it wasn't hard to come up with a thought process that would deliver an intrusion hosted deposit here. There was already indications of, you know, nickel copper anomalism here, and that apparently went unrecognised for decades. And also those early discoveries are actually outcropping mineralisation. So, you know, it's a pretty good chance that surface geochemistry in this district will work as well. Anyway, so that was, you know, the positives. I guess, you know, why didn't people persevere here? Probably, you know, conceptual targeting on the basis of just, you know, pre-competitive geophysics might seem pretty risky, and maybe everyone thought everyone else had done it before. The survey mapping didn't show any geology, so perhaps people convinced themselves we had the wrong geology for this style of deposit. There was certainly no historic mineral occurrences at Julimar, so perhaps again, you know, non-prospective setting. And maybe something like this, you know, just a simple point that the deposit was on farmland. Perhaps no one thought to go and talk to the landowners and see if they could get access. So I guess, you know, there's always reasons for and against going into an exploration project, but with Julimar, we recognised it was going to be low-cost exploration. We could get on the ground and do the types of surveys that are effective for discovering these sorts of deposits. There was a low probability of success, but with such a high reward opportunity that a company like Chalice, you know, a junior company should take those bets. and essentially we got lucky there. So in terms of our acknowledgements, again, it's what you want to see when you're on an RC rig, lots of black smoke. Again, lots of contributors, of course, to a discovery like this. Our external consultant geophysicists and petrologists who helped from almost day one. We've got a great team of guys on site and some good backup there in the office. And yeah, so it's one of those team successes that's still going strong. So thank you very much.